All right, let's go ahead and get started. Hope everybody's having a good day today. Today we're going to be continuing our study in AC circuits. We're going to be specifically studying RLC Series circuits, which is actually a dedicated chapter in your book. Hopefully you've had a chance to look at it. But whether you have or not, the RLC Series circuit is really one of the simplest forms of our most complex form of filter. And it simply involves an AC source, which for the purpose of our experiments could be a function generator on your benchtop, or it could be Diablo Canyon Nuclear Power Plant, connected to a resistor, which is in series with a capacitor, which is in series with an inductor. And we're going to go ahead and we're going to make this an iron core inductor. Those two parallel symbols just indicate that the inductor is an iron core inductor as opposed to an air core inductor or others that we'll talk about later. So obviously our source is going to have some voltage. We'll just call that E sub t, which is our source voltage. Now just to review very briefly, if we don't designate it as a peak or a peak-to-peak or an average, in other words, we just leave it as the total voltage or the source voltage, what type of voltage are we talking about? We're talking about RMS, right? So it's a root mean square voltage. And then the source has to have some frequency. And so in the United States, obviously, we generate at 60 cycles per second. So we'll give our frequency of our source as 60 cycles per second. And then we have to have a resistor, a capacitor, which then has some capacitive reactance, which is measured in ohms, and then an inductor. And to review very quickly, what unit do we measure the energy storage rating of our capacitor in? Farads. That's measured in the unit of farads. And what unit do we measure the energy storage rating of our inductor in? That unit is the unit of henries. So that's the energy storage rating of our inductor. And then, of course, we can convert that to the opposition to current flow associated with the inductive reactance of our circuit. And that's also measured in ohms. And so now we have basically three different components, all measured in terms of opposition to current flow in ohms. Okay? Now, we've already studied about RC series circuits, RC parallel circuits, RL series circuits, RL parallel circuits, and so now we've just moved one place further. We're looking at RLC, or RCL circuits. They're interchangeable, really. Okay. So as we looked at earlier in the week, I had you all do an exercise on vector analysis. And one of the keys that I've been emphasizing is the fact that to understand everything that's going on in the circuit, we generally have to draw right triangles or do what we call vector analysis. So if we draw the primary vectors that are associated with our circuit, let's start with the simplest one first. Anytime that we have a circuit where all the components are connected in series, are we going to find that voltage is the same everywhere or that current is the same everywhere? Current's going to be the same everywhere because obviously, regardless of what direction it's flowing, current only has one way to flow. Okay, so it doesn't have the ability to branch out. So when we look at our vector diagram, if we're looking at current, it's going to turn out that current is the same everywhere. In other words, the current leaving the battery or the source is equal to the current that's flowing through the resistor, which is equal to the current that's flowing in the capacitor, which is equal to the current that's flowing in the inductor. Okay? And so it's kind of just a little bit ridiculous to make it into a vector diagram because they're all arrows that have the same magnitude in the same direction. So if we drew an arrow to represent our total current, then the arrow representing the current through the resistor would be right on top of it. The arrow representing the current through the capacitor would be right on top of it. And the arrow representing the current through the inductor would be right on top of it. So our vector diagram is really a series of flat arrows. Okay, really not a vector diagram at all. But that is because of Kirchhoff's current law. Because looking back at our circuit, by Kirchhoff's current law, we know that the sum of the currents flowing into a node have to be the same as the sum of the currents leaving a node. And since we really only have one loop here, there's really only one direction for current to flow. Okay? The story changes, though, when we move over to our vector voltage diagram. So let's look at voltage. And just to simplify things, what I'm going to do is I'm going to redraw our circuit over here. I'll put the resistor, the capacitor, and the iron core inductor connected up to our AC source, which has an RMS voltage, a frequency of 60 hertz, a resistance, a capacitive reactance, and an inductive reactance. And all of these guys are measured in ohms. This is in ohms, this is in ohms, this is in ohms. Okay. Now, in the past, we have used a couple of tools to memorize whether or not current is leading voltage or voltage is leading current. Does anybody remember that acronym that we use? Eli the Iceman. So let's go ahead and just remind ourselves of Eli the Iceman. Okay, just to review, the L is a representation for an inductor, and the C is the representation for an ideal capacitor. So if we look at the Eli portion of Eli the Iceman, we can see that the voltage is leading the current by 90 degrees. Okay? If we look at the ice portion of Eli the Iceman, we can see that current is leading the voltage by 90 degrees. That's the basis for the directions of the arrow in our vector voltage diagram. Okay? So to develop the vector voltage diagram, what we do is we start out with our reference vector. Our reference vector is always going to be the voltage drop that we would measure across the resistor. So if we imagine my fingers to be the tips of a fluke multimeter for a moment, and my fingers come over here and measure the voltage across this resistor, the RMS value of the voltage measured across this resistor would be equal to the length of this line in our vector voltage diagram. Okay? Now, Eli the Iceman tells us that voltage and current are 90 degrees out of phase. It also turns out that the voltage across the resistor is out of phase with the voltage across the capacitor by 90 degrees. And so that allows us to draw an arrow which represents the voltage drop across our inductive reactance. That's going to point up. Now, why is that going to point up? The reason that that's going to point up is because inductive reactance is equal to 2 pi times the frequency of the source times the energy storage rating of the inductor in henries. Whereas the capacitive reactance is going to be equal to the inverse of 2 pi times the frequency of the source times the energy storage rating of the capacitor in henries. Okay, so you can see here that in order for us to get the ohms associated with the opposition to current flow of the inductor, in other words, these ohms, okay, we have to use this formula. Okay? When we take the inverse, then it turns out that we get a vector that points 180 degrees relative to the vector that represented our inductive reactance. So in simpler terms, the voltage is our reference, always. That never changes, okay? The voltage drop across our inductor is at 90 degrees of phase shift relative to the voltage drop across the resistor. We see this on the oscilloscope as a phase shift, okay? And then it turns out that the voltage drop across the capacitor, or EX of C, the voltage drop across the capacitive reactance, it's really the same thing, is pointing down, okay? So it turns out that when we look at the phase angle between these two vectors, in other words, the vector that represents the voltage drop across the inductor and the vector that represents the voltage drop across the capacitor, they are at how many degrees with respect to each other? 180 degrees, right. So this guy is 180 degrees. Okay, so because of the fact that that guy is 180 degrees, it turns out that we can, in our final vector diagram, which I'll just redraw here, it turns out that we can simplify our vector diagram by drawing our reference vector in the same place, that's never going to change, and then drawing a vector pointing up, and that vector is going to be the voltage across the inductor minus the voltage across the capacitor. Because they're 180 degrees out of phase with each other, you can take this guy and subtract it from this guy, and then everything points up. Now, obviously, in reality, if this guy is the exact same length as this guy, then when you subtract them, you're going to get 0. That's what we call a resonance circuit. We'll talk about that when we talk about filters. For the case now, we're going to assume that the voltage drop across the capacitor is a little bit less than the voltage drop across the inductor, which would give us a positive vector pointing up. Okay, so there's only one thing left to complete our vector voltage diagram. Anybody see what that is? That's going to be the hypotenuse of our right triangle. So the hypotenuse of our right triangle is going to represent what? The total voltage, exactly. This is going to represent the total voltage, or in our case, the source voltage. Okay? So, the total voltage in formula is going to be described by the Pythagorean theorem. So the total voltage is going to be equal to the square root of the voltage across the resistor, quantity squared, plus the voltage across the inductor minus the voltage across the capacitor, quantity squared. So it follows the same pattern that we've seen with RL circuits, RC circuits, whether they're in series or in parallel. Follows the same pattern, okay? As long as we keep in mind the Pythagorean theorem, then it's really a matter of constructing our vector diagram, simplifying our vector diagram, and then applying the Pythagorean theorem, and then basic trigonometry. Now, this angle right here, which we call theta, represents what? Well, it turns out that it can be used to calculate what we call the power factor of the circuit, which we'll talk about in a minute, okay? But what it actually represents is something that we see on the oscilloscope. In other words, if we were to draw a diagram of what we see on the oscilloscope, then if this dotted line here was the voltage across the source, in other words, if we were to put oscilloscope leads here and measure the voltage across the source, then we would find that the voltage across the capacitor, if we draw it as a solid line, will be out of phase. In other words, it will cross over the zero axis at a different place than the voltage of the source. And we call that a phase difference. That phase difference is called theta. So we can actually measure that on the oscilloscope. And it turns out that the theta that we measure on the oscilloscope will be exactly the same as the theta that we calculate in our right triangle, which represents our vector voltage diagram. Okay? Now, I'm just going to erase this to give myself a little bit of room. I'd like to talk a little bit more about the use of what we call this phase difference or phase displacement when we're talking about the overall efficiency of the circuit. We're talking about the overall efficiency of the circuit. We use the concept of what's known as the power factor to describe that. Okay? Now, there are actually two formulas that we will use in this course to calculate what the power factor is of any AC circuit. Okay? The simplest formula is the one that I think is the least abstract. And what it is the power factor, abbreviated PF, is equal to the number of watts absorbed by the circuit. Okay? And if we're talking about watts, where are we going to dissipate watts or real power in this circuit? Across the resistor. That's the only place. Now, in an actual circuit, the capacitor is going to have some resistance because it's got wires running into the plates. And the iron core inductor is going to have some resistance because it's made out of wire, and wire has resistance. Okay? But when you compare the resistance, the actual true resistance of the inductor to the inductive reactance, it's going to be negligible. In other words, it's going to be so small that you can consider it to be zero. Okay? And you basically get the same answer. So the only place that realistically we're absorbing watts is going to be across the resistor. Okay? So we're measuring the watts that are absorbed across the resistor, and then we're dividing that by the volt amperes, or the apparent power that's delivered by the source. Okay? So the source is being required to deliver energy to dissipate heat across the resistor, to create an electric field between the plates of the capacitor, and to create an expanding and collapsing magnetic field around the inductor. Okay? When we take the vector sum of all of those powers added together, what we get is the hypotenuse of a triangle, okay? And that's measured in the unit of volt amperes. Okay? So if we take watts and we divide it by volt amperes, we get power factor. So let's imagine for a moment that our watts were equal to our volt amperes. In other words, let's just say that we measured 500 watts being absorbed here, okay? And we measured 500 volt amperes being delivered by the source. Then our power factor would be equal to 500 over 500, which is equal to 1. So that's what we call a unity power factor. So any time that some of the power that's coming from the source is being delivered to other than the resistor, like the capacitor or the inductor, we get a power factor that's less than 1, like 0.9 or 0.8 or 0.7 or 0.6 or 0.5 or 0.4 or all the way down to 0. Okay? There is another formula that's used quite widely in the power industry to measure power factor directly off of the waveforms that we get from the oscilloscope. So if we measure what this phase angle is, or the phase difference between the two waveforms are here on the oscilloscope, then all we have to do is take that angle and take the cosine of that angle, and that will give us the power factor, okay? So if we had, worst case scenario, a 90-degree phase shift, what's the cosine of 90? Cosine of 90 is 1. So if we had the cosine of 90 degrees, that would be equal to 1.0. So you can kind of see that if you look at, kind of a worst or best case scenario, however you want to look at it, you really get the same answer, regardless of whether or not you use the formula that says power factor equals watts over volt amperes, or true power over apparent power, or you use the formula that says power factor is equal to the cosine of the angle that we find in this triangle, or the angle that we find on the oscilloscope between these two waveforms. Do you have a question, Adrian?
The first one is called unity field.
It's called unity power factor. Unity power factor. So this guy would be a unity just meaning 1. Unity power factor. So that would be a unity power factor. Now, very rarely do we find a unity power factor in industry. If we went back to the pad mount transformer that's located outside of this building, and we were to use a $4,000 or $5,000 Fluke power harmonic analyzer that could very accurately measure the power factor that was associated with that transformer feeding this building, we would find that the power factor was probably around 0.7, 0.75, 0.78, somewhere in there. Somewhere between 0.7 and 0.8. Now, if we wanted to make it better, in other words, closer to a unity power factor, which for our purposes would be as efficient as we can get, okay, what we would have to do is we would have to add capacitors in parallel with the circuit. So in other words, if we found that this circuit right here, let's just say hypothetically, had a power factor that was equal to 0.78, okay, then what we could do to correct that power factor of 0.78 and get it closer to a unity power factor, or a power factor of 1.0, is to physically place a capacitor in parallel with this entire load. And what that does is it causes the capacitive reactance of the whole circuit to change. Okay? In reality, what we're doing is we're supplying reactive VARs from this capacitor. So we find that there's a current that circulates back and forth around this loop right here. Okay? And if you have a capacitor to supply that current around this loop right here, then as soon as you've energized that capacitor, you no longer have to supply that current. So let me give you an example of what I've seen personally in industry. I've seen situations where we've gone into a facility, we've measured a power factor of something like 0.78, okay, even worse. I've seen power factors of 0.5, 0.4, 0.3, okay? But usually you'll see it about 0.7, okay? And what we'll do in reality is we'll put a switch, and generally that switch actually is physically a relay. So we'll put a switch into the circuit so that we can either have the capacitor inserted into the circuit, or we can have the capacitor out of the circuit, okay? And so what I've done on several occasions is I've taken a clamp-on Hall effect ammeter, okay, which is a meter that just clamps onto the cable down here and then displays current. So let's say that this was drawing 1,200 amps. Okay, so we clamped a meter onto this cable down here when the capacitor was not inserted into the circuit. And upon doing that, we saw that the power factor was 0.78, and the current that we were drawing from Diablo nuclear power plant or whatever source we were using was 1,200 amps. Okay? Then what we do is subsequently turn on the field circuit to our relay, which has the effect of closing the circuit or closing the switch. So if we just show what the effect of that is, basically we're just closing in the switch here, which puts the capacitor in parallel with our entire load. I've seen this number change from 1,200 to 500. Okay? Now, if you're paying the electric bill, do you want to pay for 1,200 amps being sucked into your building, or would you prefer to pay for 500 amps being sucked into your building? You'd much prefer for 500 amps to be sucked into your building, because that's going to determine ultimately what you're going to pay for your electric bill. So the people that are paying the bills, chief financial officers, may know nothing about electricity, but have been explained, it's been explained to them that current is a big part of what makes up their electric bill. And they see the electric bill coming in every month, and then you show them, well, gee, if we don't correct the power factor, you're going to be sucking 1,200 amps into your transformer. If we do correct the power factor, we're going to be sucking in, we're going to change this number to 500 amps. Hoorah! Okay? The big determination as to whether or not companies will pay for you to do this is what the payback is. Okay? What I mean by payback is how long it's going to take the company to recoup its investment in terms of monthly savings. So let's say that it's going to cost them $35,000 to put in the capacitor and all of the controls to switch the capacitor with the relays and all. It's going to cost them $35,000, okay? But let's say that we look at their bills and we realize that it's going to save them $12,000 a month. 12, 24, 36. They paid for their investment in 3 months. That's a no-brainer. That's one that they'll jump on in the worst economic times, okay? Because it's such a quick payback. A lot of companies will have a policy that if something doesn't pay for itself within 3 years, they're not going to do it because they just don't have the capital to do it. But if you bring something to them that'll pay for itself in 3 or 4 months, it's like, where do I sign the check? Okay? So there are a lot of electrical engineering contractors and also electricians that have their C10 license that get into this business exclusively, where all they're doing is coming into the building, measuring and documenting how much power they're drawing when everything's on in the building and when there's, minimal lighting and security systems on in the evening when everybody's gone home. Okay? Figuring out what the monthly bills are, or taking a look at historically what the monthly bills have been, and then doing a power factor analysis to figure out what the power factor currently is during high peak loading, and then what it would cost to get the power factor as close to unity as possible. Okay? And the reason that it's a little bit more sophisticated or difficult than just hardwiring in a capacitor is because the amount of farads or the amount of capacitive reactance that needs to be in parallel with the load is going to change every time you turn on a new load. Okay? So let's say that you have a compressor up on the roof that's part of your HVAC system, right? And this compressor is huge. Every time that compressor cycles on, the power factor is going to change. Every time somebody turns the lights on in the northeast end of the building, the power factor is going to change. Every time somebody turns on the motor for the roll-up doors, the power factor is going to change. So you have to have circuitry that's sensing what the power factor is in real time, and then it's switching in whatever capacitance is necessary to offset, okay, that power factor. And so in reality, what we end up with is a rack of capacitors that are in series and parallel configurations with each other. And so we end up with, you know, like a C1, a C2, a C3, and then in between all of those capacitors, we have relays. And we're able to switch those capacitors on and off so that we don't exceed a unity power factor. Okay? The problem with getting exactly to unity is that you can form what we call a parallel or series resonant circuit. Okay? For those of you that remember back to high school, there's an example that's used in high school physics books with a bridge that fell down called the Tacoma's Narrows Bridge. And that bridge fell down because of basically wind that started it oscillating. So the thing started oscillating, and everything has what we refer to as a natural frequency. So you can take a spring, and you can take, you know, just a very lightweight spring, nothing like you'd have in a car. A very lightweight spring that you could, you know, pull with your fingers. And you can hook a weight onto it, you know, like a fishing anchor. All right? And then you can pull that thing down, and as long as you have it secured to a rigid platform, which could be your finger, you let that thing go. What's going to happen is the spring is going to oscillate. Doing, 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 doing. Well, if you stand there and you count it, you can figure out how many cycles per second that thing is oscillating at if there's nothing else pulling on it except gravity. That would be the natural frequency of that spring. And so in physics experiments, what we'll do is we'll take a rigid platform, we'll hang a spring from it, so it'll look like this. We'll have a rigid platform, we'll hang a spring from it, and then we'll put a weight on the spring. Okay? Putting a weight on the spring creates a gravitational force pulling down on the spring, and then what happens is the spring begins oscillating back and forth, back and forth, back and forth. Okay, so even by inspection, you could get a fairly accurate count of the number of cycles per second that the spring was oscillating at. That would be what's known as the natural frequency of the spring. Now, if you were to take a motor, take another rigid platform, and take a pulley on a motor and physically attach it to the spring. Take a little piece of twine, wrap it around the spring. So you start tugging on the spring as the spring is moving at its natural frequency. What happens is, let's just say hypothetically that this was 20 cycles per second. That was the natural frequency. Okay? If you adjust this, the frequency of this string that's pulling down on the spring to the same frequency as the natural frequency of the spring, which would be 20 hertz, what happens is the spring goes crazy. if you look at it mathematically, it's actually a fairly complex formula. But what it turns out to be is a formula that predicts what the amplitude of the oscillation is going to be. And when you look at that formula, what it is that you get that's very interesting is you get a formula that says the amplitude of my oscillation is going to be equal to some number divided by 0. I don't mean to say theta there. I mean to say 0. Okay? So what's division by 0? Infinity, or undefined, depending on how complex your mathematical background is. So what it's telling you is that this thing is basically going to tear itself apart, because you're not going to be able to get infinite oscillations. I mean, that's just an expression in mathematics that's used to basically say that the thing's going to tear itself apart. So what it is that happened at the Tacoma Narrows Bridge is that the bridge started oscillating, and it just so happened that it hit its natural resonant frequency. And so the magnitude of the oscillations just started going crazy until it got so big that it literally tore itself apart. If you actually look at the whole story, there was a car on the bridge. Some old car, it was like in the 30s or something. And there was a guy in the car. The bridge started oscillating. His car stalled. I don't know if it was due to the oscillations or just his car not being in good shape. He got out of the car. He ran to the end of the bridge so that he got off the bridge in a place of safety. And then his car, and unfortunately his dog that was in the car, went down with the bridge. So now what they do when they build bridges is they figure out what the natural frequency of the bridge is, so that if it ever starts to oscillate at any frequency that's close to that, there are sensors that dampen the oscillations, just like on an airplane, just like a wing on an airplane. They think of bridges like wings on an airplane. That's how structural engineers think of bridges. They think of bridges like wings on an airplane. And they make sure that if they ever get close to their natural frequency, there's something there to dampen the oscillation so that it doesn't tear itself apart. So we have never had a repeat of the Tacoma Narrows Bridge. But the concept carries over into the study of electrical engineering. Okay?
Did you have a machine that just did that and made energy?
Yeah. I actually took a physics class where we had a little pulley that was hooked up to a motor. It was like a sewing machine motor, right? And so we could determine how fast the pulley was going to spin around by turning a knob, which was connected to a variable speed drive. And so as a result, we could change the frequency that we yanked on the spring. And it's very interesting because you'll see the springs start out like this, and then when you hit the natural frequency and you're tugging on it, it starts doing this, and then all of a sudden the spring's just stretched out and it's, effectively non-operable. So that same philosophy that applies to a mechanical system also applies to an electrical system. So if you get into a resonant condition in an electrical system and you don't intend to be there, then you can actually do more harm than good. So that's why you have to be very, very careful before you put in power factor correction to make sure that you haven't created a series or parallel resonant circuit. Okay? So we'll talk about that some more as we continue our studies. But in terms of our voltage vector diagrams, the same thing would apply that we studied with the RC series, RC parallel, RL series, RL parallel, and that would be that we would have a current vector diagram. In our case, it was a very simple diagram, just one straight arrow, all equal to each other, okay? A voltage vector diagram, a power vector diagram, and an impedance vector diagram. And all of those could be used to calculate any electrical quantity that you want to. And all of the formulas are summarized in the back of your book I believe it's page 1070. Somebody want to correct me on that? It's around there. It's around page 1070. So if you look back in your appendix, you will find all the formulas for RLC series circuits. Now the formula to figure out what value of capacitance you need to stick in here is something that we'll be talking about at a later time in a subsequent lecture. Okay, any questions? All right, well, it's about time to quit, so everybody drive safely, and I'll see you tomorrow.